Hey guys, welcome back to another video, and today would be doing a different topic, which is graph theory. So I've taken graph theory as my master's course, so I would be covering different topics of it. So this video is all about the basics. So we'll be looking into what graphs are, how graphs are made, and some of the basic stuff related to graphs. So the first thing that we need to know here is what is a graph, right? So a graph is a combination of vertices and edges, which we write in this format. So V here represents vertex and E represents edges. So the plural of vertex is vertices. Anyway, so vertices are basically, these are entities inside of that graph, and edges, they represent the relationship between these vertices. Like, for example, you can think of it in a way that, let's say this is your father and he's connected with his mother, and he's also connected with you, the son or the daughter, and you're connected to your friends, right? So these are vertex, this is the relationship, so this is the edge. So this is basically, the whole thing is a graph. Okay, so graphs can be of different types. They can be, as far as I know, is of three types. So one is based on the weight, where we have two things. So one is a weighted graph and another one is a unweighted graph. So let's just see an example here. So we have a graph where we have three vertices, A, B and C. A is connected to B and C. So the weights, let's say we give 5 and 4. So what this says is, if we want to go from A to B, we need to go 5 steps, or the weight is 5 steps. Or we want to go from A to C, we need to take 4 steps. And unweighted graphs are basically the graphs that we showed here. So if you go from, we have three vertices A, B and C, and see, they do not have any weights. So you can go from A to B and B to C. So there is no concept of how much steps or how much money you would take if you think about weights in a certain criteria. So this, they don't require anything. Now coming to the second classification, this is based on direction. And in based on direction we have two. So one is directed graph and another one is undirected graph. So a directed graph is basically, there would be like symbols. So we have, let's say again, three nodes here. So there's only one path from A to B, so you can go directly from A to B, and we have path from B to C. Look at the previous graphs, they do not have any direction, so it's just one line. But in directed graphs we have a direction, so we can only go from A to B. And in undirected graphs, so this is the examples of undirected graph. So A to B, then to, let's say, C. So what this is implying is that we can go from A to B, then we can also go from B to A, B to C, C to B. So this is like a bidirectional path. On the other hand, based on direction, so directed graphs, they have only one path, so it's based on the direction the edge points to. And finally we have the third one, which is based on edge multiplicity. So this here we have two types again. So one is a simple graph, another one is not unsimple, it's multi-graph. So a simple graph, so it's basically the graphs that we've been looking into. So A to B, B to C. So these are examples of simple graphs, right? And in multi-graph we would see the concept of self loops. So we would see, let's say we have A to B, B to C. C can go to himself again, and C can go to, let's say, D, then D can point to B, A can point to himself again. So this is an example of a multigraph where we would see self loops. So this is a self loop, and a self loop is basically we can go from A to B, right? So we can go from A to B, and we can also go from A to itself again. So you might think, when would this be necessary? So let's say A calculates a value, and that value is your own input again. So in those cases you would see self loop, but we would look into much more deeper examples of self loop as we go on with more videos of it. So the next topic is neighbors. So when we are saying that A is connected to B and C, and let's say C is connected to D, and let's say D is connected to E and F, right? So here B and C are the neighbors of A, D is the neighbor of C, E and F are the neighbors of D. So ones that you're directly connected to are your neighbors, right? So you can say that these are the neighbors of A, these two are the neighbors of D, so these two are the neighbors of B. Now there's one thing we need to know, is the concept of cousins. So the ones that you're directly connected to, so in this case we have B and C, which are your neighbors, are your first cousins. So we have first cousin, and we have the concept of a second cousin. So the first cousins are basically the ones that you're directly connected to, or your neighbors, and second cousins are the ones that you have to go through your first cousin. So in this case we have B and C, these are your first cousins, and D would be your second cousin, because when we want to go to D we have to go from A to its first cousin, which is C. Now D is the first cousin of C, right? So when we go to C, and from C we can go to his first cousin, which is D. So this D is the second cousin of A. Now there's one more interesting thing that we need to talk about, is matrix. A graph can be represented through a matrix, and there's one thing that you have to always remember, is undirected graphs, they generate a symmetric matrix. On the other hand, directed graphs sometimes create symmetric matrix based on how they are built. So what does that mean? So let's just try to create our own graph here. Won't be putting a lot of nodes here. Okay, so this is like a simple 4 vertex graph, and we are trying to put that into a matrix. So remember, the matrix would always have to be an n into n, where n represents the number of vertices. So this would be a 4 by 4 matrix, because we have 4 vertices, and let's put their names down. So A, B, C and D, and we have, let's say, A, B, C and D, right? So do we have any connections from A to A? So no. Then A to B, yes. So 1 represents yes and 0 is no. A to D, A to C, yes. A to D, no. So this is basically the first cousins, or the neighbors. So B has a connection to A, doesn't have a connection to itself. B to C and D. C has a connection to A, B, and no one else, and D has a connection to only B. So if you look here, this is a symmetric matrix, because symmetric matrices are basically the matrices that you do a transpose of, and they would return the same thing again. If you look into here, if you look into the line here, so if we write that line down, you would see that there is always a match here. So this is basically a symmetric matrix, and undirected graphs, they always would generate a symmetric matrix. We would be covering another part of graphs, which is called components. So let's say we have a graph here which is A, B, C, D. Okay, so this whole thing is a graph, and this graph has only one component. So what do we mean by this component? So the whole thing itself is a component. However, let's say we have two more edges that are connected to one another, but we are saying that this whole thing is a graph. Then we would have two components, because we have one thing here, so which is one small graph. We have another thing here which is another small graph, but these graphs, they are not connected to one another. Thus in the main graph we would have two components. So let me write it down again. So we have A to B and to D, and we have E to F, right? So the whole thing, we're saying that this whole thing is a graph, but as these two things, so this is, let's say, component 1 and component 2, as these two components, they're not connected to one another, they're still a graph, they're small subgraphs, but we can say they are separate components. However, in a scenario, let's say we connect them to one another, so let's say D is connected to E, then are they their separate subgraphs? No, they are connected to one another, so the whole thing becomes one graph. Thus there would be only one component in the whole graph, which is the whole thing. Let's just try to look into another example if this is a bit confusing. So we have A. Okay, so in this example, so we are saying that they are separate graphs. If we say they are separate graphs, how many components do each one of them have? So let's say this is graph 1 and this is graph 2, right? So let's just look into graph 1. Does graph 1 have other edges or other nodes that are not connected to one another? So let's say we have these two vertices that are not connected to, let's say, D or any one of the other vertices here. Now if that's not the case, then this whole thing, all the nodes, they are connected to one another, so then that means this graph has only one component. And in graph 2, do we have nodes that are not connected to one another, so nodes that are separate, that where we can say this is a smaller subgraph? So if you look into here, we do not see that, right? So all the nodes, they are connected to one another. However, let's say we have a situation where we have this. So in graph 2, we can see there are nodes that are not connected to one another. So there are nodes that we can say there are a standalone graph, right? So we can say this is a standalone graph, we can say this is a standalone graph. So this, both are subgraphs of the main graph 2, right? However, let's say we do not want components here. So what we do is we connect them. So when we are connecting them, we can see that we do not have separate subgraphs of the main graph, rather we have only one whole completely connected graph where all the nodes, they are connected. So remember, we are just putting these two lines that are making the whole graph connected, not having any subgraphs. However, let's say we remove these two, then what do we have? We have separate subgraphs. So this is the concept of components. So let's just try to see another interesting example here, or interesting theory. So what the theory says is, when a graph doesn't have any edges, then component number is equal to the vertex number. Okay, so let's say we have a graph with 4 vertices, so A, B, C and D. So in this graph, can we say there are 4 components? Yes, we can, because they can be their own separate subgraphs, right? Okay, so other than that, so as the theorem says, when a graph doesn't have any edges, the component number is equal to vertex number. So let's say the component number here would be equal to the vertex number. So the vertex number is 4, right? And which is what we said here, right? So we do not have any subgraphs, so there would be 4 components, which is equal to the vertex number. However, let's say we connect C and D together. So let's read the theorem again. When a graph doesn't have any edges, so we do have edges, we have one edge. So when we have one edge, we then have how many components? So 1, 2 and 3, right? Because the whole graph isn't connected, and we can say this these 3 things can be their own separate graphs or subgraphs. So we have 3 components now. So C equals to the number of vertices, but these 2 are connected, so C reduces by 1. Then if we somehow connect A and C together, can we say that this whole thing becomes this becomes a connected, right? So this can be said as its own subgraph, and B is another subgraph, right? So as these 3 vertices are connected, so we would have only 2 components, so 1 and 2. And finally, let's say we connect A and B together. Rather than that, just try to connect A and D. So does this increase or decrease the number of components on the graph? If we look into here, we can see, if we remove all these green lines here, we can see that first we had this connection, meaning that we had only 2 components in the whole graph, one here, another one here, because they're their own subgraphs. However, when we're making this new line, right, does this decrease the number of subgraphs? No, it doesn't, because it's still this one and this one. So subgraph 1 and subgraph 2 doesn't decrease the number of components in the graph, right? That's why this new edge doesn't bring anything new to the table. It just makes another connection that we already had. So we already had a path from path to go from A to D or D to A, right? This one. We just made another path from directly going from A to D. This doesn't increase the number of subgraphs or decrease it. However, when we, let's say, connect this, what this is doing is connecting the whole graph. We do not have any more subgraphs. So all of the nodes, they're connected to one another. So we can go from A to D to B, or C to D to B, right? All of those nodes are there connected. So this whole thing represents a graph. It's not a subgraph anymore. Then the component number would reach 1. So that's all from the basics. So this is like the part 1 basics of graph, and we'll be doing another small video where we'll be looking into some other things that are the basics of graph. So that would be part 2. So thank you for watching the video. Hope you guys liked it, and if you have any comments or suggestions, feel free to comment down below. Thank you.